This is called mathematical
Where's Connor?
induction. Don't worry about it. Don't distract me. Don't ask any question that isn't about this. Mathematical induction. Okay? Mathematical induction is a truly weird idea, and I swear it works, but you wouldn't know it. It is a form of proof. It is a form of proof. If you hear the word proof, it makes you a little nervous. Makes you think back to those days of geometry and two columns and all that sort of thing. And that, doesn't make you feel good. This will make you feel better about proof, because this is a lot harder. Okay, mathematical induction says, given an algebraic statement or premise, and these algebraic statement or premises are going to be informed in the form of some of the statements that we've been talking about. The sum of the first nth terms of a series, or something like that. Okay? Give it an algebraic statement or premise. 1. Verify its truth for n equals 1. 2. Verify. This one's a little harder to say. Verify that you know what? I'm just going to show you the process. Verify its truth for its n plus 1 term in terms of its nth term. Raise your hand if I've said anything that makes sense so far.
Totally.
It's okay. You guys are brave or liars. Verify its truth for n equals 1. Verify its truth for the n plus 1 term in terms of its nth term. Thank you, Saul. I'm looking forward to it. First example is, okay, we are going to do a fairly simple one. Okay? Example. Prove that 1 plus 2 plus 3 plus 4 plus ... going up as far as you want, all the way out to the nth term, equals n times n plus 1 over 2. This is the second formula you've learned for this. The first one was Little Carl's method with the n over 2 and the a sub 1 plus a sub n. But these formulas are also just in terms of the number of terms. Okay, you don't have to notice you don't have to figure out the first term or the last term. All you have to know is how many terms you want to add up. So that's a little bit different. We're going to prove that this is true for any term you can imagine. Okay? So, first thing we're going to do. Question 1. Is this statement true when n equals 1? Okay, this is not a trick question, but it can be confusing. This is a, okay, you guys get that this is a sequence. Okay? What is the sum of the first n terms? What's the sum of the first term? 1. It's just 1. Okay? Does this formula correctly give us the sum of the first 1 term?
Does that mean you plug 1 into n?
Yep, put 1 in for n.
Yeah.
N plus, then 1 times 1 plus 1 over 2 equals 2 over 2 equals 1. Check. Step 1 taken care of.
Wait, but it doesn't do it for that.
Well, now, here's the next one. Prove its truth for the nth plus 1 term in terms of its nth term. There's a couple of ways to do this.
Would that be 3 though?
No, it's a little weirder than that because we're not going to plug in a value. And your book uses k. Okay? So here's what I'm going to do. The sum of the kth term, I love saying that, putting k in for n, according to this formula, would be k times k plus 1 over 2. If k were 5, I'd put 5 in for n. If k were 27, I'd put 27 in for n.
Well, how do you know what k is?
Well, we don't, that's the thing. We got to prove this for any two numbers we can imagine.
Wait, why is
Maybe
one
any
n and why
two
is one k?
numbers.
When they n, okay. Here's what your book's thinking. Stay with me.
I think
This is a big problem because at younger ages, you guys aren't truly taught well, and I don't do a great job of it either, but I try to learn the difference between a constant and a variable, an unknown constant.
n is a variable and k is a constant.
Yes. So n is supposed to represent any number of terms you can imagine. K is some specific one you have in mind.
So then you add them up.
Well, no, we're not going to add them up. We're going to do something a little crazier here. So, follow me on this one. The sum of k plus 1, if this is 4, this is 5. If this is 200, this is 201. If this is 1 gabillion, this is a gabillion and 1.
If it's infinity, it's infinity.
Infinity really doesn't work that way, but I like that you went there, Johnny.
Infinity and beyond.
So now this is k plus 1 times k plus 2 over 2. Would this be the k? Is this one way to write the k plus 1th term if this is the k term?
What the?
I've made k one bigger here, here, and here.
So if k was 1, it would be 2 plus 1 and then 2 plus 2?
Yep.
Oh, okay.
Okay, now, this has to be a general proof. We've got to prove this works for any numbers you can imagine. One way to look at this is, I heard an analogy, I read it in an algebra history book that I liked. I don't know if I can say it well enough to make sense. The idea behind mathematical induction is you're imagining a ladder that goes up to infinity, and the rungs are evenly spaced, which means if you figure out something is true about any two consecutive rungs on the ladder, it must be true about all the rungs on the ladder. So if we can prove something is true about any two rungs on this ladder going up to the possibility of infinity, then it will be true out to infinity.
That's a really long ladder.
It is a really long ladder.
That makes sense.
There's a
That has no practical application besides math, though.
cryptology, code breaking, prime number searches, which admittedly is just about math.
Yeah, but I'm talking about, like, objects.
Yeah, you can. That's true. You know you can.
Ladders are always different.
I won't lie to you. You can build computers. You can send a man to the moon, and you can build entire cities without really using this. But there's a couple other things where it does come in handy, and they are mostly abstract.
Oh, really? Easy?
Yes.
So
Now,
we need to
so
know
here,
this?
here's what I'm going to do. Okay, I'm going to say that the sum of all the k terms plus. I don't want to write this. I'm going to write it this way. Okay, hang on.
Lord of mercy.
The sum of all the k terms is k times k plus 1 over 2, right? This adds up, if k is 5, this is what all the first 5 terms add up to, right?
Yeah.
If k is 27, this is the sum of the first 27 terms.
Sure.
I'm going to add the next term to this.
Wait, does that still equal S of K?
Yeah, this half equals s of k.
Oh.
But now I'm going to add the next number. So if this is the sum of the first 5 digits, then this must be 6.
Right.
If this is the sum of the first 200 digits, this k plus 1 must be 201.
Wait, say that again.
Okay, here's my sum. Here's what I'm guessing. Here's my guess. I haven't proven it yet. This is what I think is the sum of the first k digits.
Okay.
So if k is 5, this should get me 1 plus 2 plus 3 plus 4 plus 5.
Okay.
If k is 100, this should get me 1 plus 2 plus 3 ... plus 99 plus 100. To this, I'm going to add the next term, whatever it is. So if k is 100, this will get me add up all the terms from 1 to 100, and then I'm going to add 101 to that. All right? If this formula works, then this will get me the same thing as this, which is my sum for 101 terms. Okay?
It's like you're working backwards.
Should we just...
Strangely.
Couldn't we just write S, K, 1?
Yeah, I could just write S sub k